Okay, so welcome to today's lecture of sys-prog. Today's topic, compilers. So, as a quick overview of today, what we will see is an introduction to LLVM. So this includes parsers, optimizations, and sanitizers. We will not learn how to build an entire compiler from scratch. Because we will not look at the front end, so the parsing, and we will also not look at the actual code generation in the backend. So first, an overview of LLVM. So LLVM is a compiler framework. It is not a compiler by itself. It is developed by Chris Lettner, and it is a framework to build compilers. So it's a collection of modular and reusable compiler pieces that you can then string together depending on your use case to a compiler. So a compiler usually has three phases. You have a front end, you have a middle end, and you have a back end. And in the front end, you parse your high-level language like C down to a single intermediate representation, which for LLVM is LLVM IR. Then in the middle end, you perform optimizations and analysis on that IR. And in the end, your backend will lower this IR again to your actual target code. Now, let's take a closer look at LLVM IR. So LLVM IR is a strongly typed intermediate representation with quite well-defined semantics. So it is in static single assignment or SSA form, which simply means that you have an infinite set of registers, and each register you can write exactly once. It is designed for usage in the middle end specifically, so for analysis and optimizations. It is not meant for front end or back end. So we can look at an example. So you have this add function, which basically just sums two numbers and returns the value in C. And in LLVM, it looks quite familiar. So you still have a function definition of this add1 function, takes as an input two integers, adds them through an add operation, and then returns the value from that. LLVM IR is structured in a really nice way. So on the outermost layer, you have a module, which is your entire translation unit. So which is basically one C file that you have in your code is one module. A module contains functions, which are just pieces of code that you give a name to, and you can also uniquely identify through that name. Functions contain basic blocks. Basic blocks are just linear sequences of instructions without control flow, and instructions themselves are just simple operations, like this add we have seen before. You can take a look at LLVM IR and how your C code, for example, gets transformed to LLVM IR by running a command like this. Yes. So, if we take a closer look at instructions specifically, they always have a similar form. So on the right-hand side of the assignment, we have the instruction itself, which has a name, which defines the semantics of that instruction, in this case an add. We have types. In this case, this is a single type for both the operands and the return value. We have a list of operands, so all of the values that go into the operation. And we have a possibly infinite list of metadata for each instruction. Metadata doesn't change the meaning of an instruction. It's just some information that an optimization pass can use to possibly transform an instruction in a different way. And then on the left-hand side, we have those virtual registers. Again, you have infinitely many of them, and they are only written once. So each virtual register uniquely identifies the operation that writes to it. So we can also take a look at control flow, which in LLVM IR is a little bit different than in C. So in C, you have very structured control flow. For example, you have an if, then else, and you have a then block and a separate else block. Yeah, in LLVM IR, everything is flat. So you only have basic blocks and branch operations that basically form the control flow between them. Nothing is nested, everything is on the same level. So if we go through and we compare both sides, you have this comparison operator, which compares something to 0. And then based on that, we make the decision where we want to branch to. In the then block, which now is its separate basic block, we do this addition with 1. In the else block, we do the addition by 2. Now, since we can never overwrite the value in a register, we need an operation that says we would like to choose a value depending on which branch we took. And this is exactly what this phi node does. This phi node is basically just there to say if we took the then branch, then now our value is the value in register 0. And if we took the else branch, we take the value from register 1. Function calls work pretty much the same way you know from C. So again, the function is identified by its name, so you can just call a function by its name, you pass inputs, and you get a return value out. Now, let's take a look at LLVM parses. So LLVM parses run on different IR constructs. Yeah, this could be a function, this could be an entire module, this could be individual instructions that make up a loop, or something else. So in the middle end, right, which is what we focus on, parses are pretty much self-contained. They are a single optimization, a single analysis that you then in your pipeline can place at an arbitrary point. Yeah, and you can combine and different parses to an arbitrary list in your pipeline. Parses but may depend on some analysis that is done by another parse, which then gives you some kind of dependencies between parses. Parses or analysis always take valid IR as an input, and they will always produce valid IR. And of course, kind of important for the task that you will do this week, you don't need to recompile your compiler every time you want to add a parse. No, you can specify parses as standalone plugins that you can then just pass to this opt tool to actually run on a piece of IR. So the most simple parse that you can do is this hello world parse. So that's an existing example from the LLVM project. And it's a simple parse running on a function, which basically just counts the number of instructions in that function. So as an input, you get a function. A function is just a collection of basic blocks, so you can iterate over all basic blocks in a function. And a basic block is just a sequence of instructions. So again, for each basic block, you just iterate over all of the instructions in it, giving you basically an iterator over all instructions in a function. You just count up a number and you print that as a result. Easy. What you will see in more complex parses is this visitor pattern. So you of course can do this trivial thing, what we've just seen, and where you iterate over every instruction in a function. And then you check if it's actually an instruction that you care about. That's pretty inefficient. So instead, what LLVM gives you is this visitor pattern. So the visitor pattern, again, automatically iterates over all, say, instructions in some container, in this case a function, and it exposes to you specific functions that you can override, which will only be called on a specific type of instruction. So in this case, we have a specific implementation for the visit load instruction and a specific override for the visit division function. Which means that should your function contain either a load instruction or this division, then those those new functions will be called. For every other instruction, which is not a load and not a division, you have this generic visit instruction function. Now, this is a very clean way of iterating over instructions and filtering at the same time. So what you can do with this is you can very easily rewrite patterns. So as an example, we have a simple pass that replaces some instructions with semantically equivalent instructions, just in a different combination. So this is an example from the Hacker slide book. And it's really just an example to show you how passes work. This is not an optimization that is useful in any way. It's just an example. And what we want to do is we want to replace this division by 2, which has an addition as input. We will replace that with this AND XOR shift left and plus combination. Yeah? So your original program might look like this, where you have X and Y, which are just arbitrary values, and then you have this pattern of addition and division by 2, which we want to replace. So how this would look like in a pass is, of course, you use a visitor and you override the visitor specifically for this division, right? Because in your original pattern that you want to match against, the division is the outermost operation. So once you have a division instruction, you need to check if it's actually is the root of the pattern that you want to match against. So you get the operands of the division instruction, and then you check is one of them a constant integer and it has the value 2, and then for the other one, is it an add operation? Right? If that is the case, you have found your pattern, you can continue. If that's not the case, well, then you just found an arbitrary division instruction, you don't care. Once you have identified your pattern, you get your X and Y, which are just the inputs to the add operation. And then you can start to build your new pattern. So for that, LLVM gives you this builder abstraction, which lets you very easily create and chain individual instructions. So we will just build an AND, an XOR, a shift left, and a result. Yes, so on the right you would see the LLVM instructions that you will produce through the calls through the to the builder. And then what your pass needs to do at the end is all uses of the results of the original division instruction you will now replace with the result that you produce in your new pattern. Has one drawback, and that is after you replaced the uses, the original instructions still exist. Yeah, so your LLVM code might look like this. The instructions that are marked in red are the original instructions, yeah, the add of X and Y and then division by 2. Those are the old instructions, and everything in between is the pattern you just built. So now you have replaced all of the uses of the original division by the results of your add, of your final add, which means this division is now considered dead. A dead instruction is basically just an instruction whose results are not used anywhere else, and it doesn't have side effects. So loads and stores would be memory accesses, those have side effects. A division doesn't have side effects. So in this case, this division is dead, right? Which means you can safely remove it. Which in turn means that the original add operation, which again is the one marked in red, also is dead, right? Because now its value is not used anywhere else. So now, after removing the division, you can also safely remove the add. And this is Just simple dead code elimination, a very common pass that you will find in compilers. So, next part is sanitizers. So sanitizers are essentially debugging tools. So you have something like an address sanitizer that gives you information about buffer overflows and use after freeze. You have the thread sanitizer, which lets you debug deadlocks and data races, and you have the memory sanitizer for uninitialized memory. Sanitizers always have two components. So you have the compiler side, which is compiler instrumentation, and you have a runtime library, which actually executes code when you run your original program. So the first part, the instrumentation, is of course something you can implement as a compiler pass. So in the case of a very simple address sanitizer, you would instrument all function calls to functions that handle memory, so like a malloc and a free. And you would also instrument all operations that touch memory, so like a load or store. So you would transform your initial LLVM IR, which just calls malloc and then stores to the resulting pointer. You would transform to the code below, where you now call a runtime malloc, which is defined in the sanitizer's external library. And you would instrument the store by calling a runtime check before you do the store. This runtime check is again a runtime function, not part of the original code, but it's part of the sanitizer's runtime code. And you pass it the pointer that you want to check, and you give it some additional metadata like the access size of the store you want to perform. Yeah, this is the compiler side. Everything here happens at compile time. Then at runtime, your resulting program will do those runtime function calls, right? So what happens initially for the address sanitizer at least is that we want to keep access information for every byte of memory, right? So we need to initialize something we call shadow memory. And the idea is you can simply abstract each byte of memory in a single bit. So you need at most 1/8 of the total address space to keep your information. Then, say your program allocates memory, which now that you have overwritten the malloc with the runtime malloc, you can specify what should happen at runtime. So first of all, you of course need to allocate real memory to give back to the program, but the address sanitizer adds some padding around. And then in your shadow memory, you can mark your original allocation as accessible and the padding as inaccessible. And the idea is that once you do a runtime check of a memory access, you query this shadow memory, right? If you access the original memory, then everything's fine. If you access the padding, that means you have an out of bounds access and it should fail. And of course, the point of the address sanitizer is it shouldn't just fail. No, it should give you an error message. So you handle this fail in a nice way. And then, of course, just to complete everything, if you have a free, which is now overwritten by your runtime free, you just mark everything as inaccessible. Should you then again have a runtime check, this would basically tell you, oh, this is a use after free. Yeah, very simple. So with that, we are done with sanitizers. And in the end, I would like to give a little bit of an outlook what is happening in compilers right now, and that is MLIR. So MLIR, the idea behind that is that LLVM IR is really not a suitable abstraction for all transformations that you can think of. Yeah, it is flat, it is low level, it is somewhat close to hardware, which makes it hard to implement optimizations that work on a higher level. Yeah, so there are a lot of optimizations that would benefit from a different abstraction. So, for example, ML, the original use case for MLIR, prefers high-level tensor types. So a data type that tells you how your data is laid out in memory. Now, it doesn't exist in LLVM IR, so you cannot abstract that. Also, something like OpenMP, which you use in HPC, benefits from affine loops and structured control flow. Yeah? Structured control flow, again, something that doesn't exist in LLVM IR. Everything is flat. And then there's a arbitrary long list of optimizations or use cases you can think of that benefit from a higher abstraction than LLVM. Problem is, for each of those abstractions, you don't want to build an entire new compiler or entire new compiler pipeline. Yeah, you want to reuse as much as possible, so those different abstractions should be somehow composable. And this is where MLIR comes in. MLIR is basically a template IR. So this base MLIR you can extend by adding dialects on top. And each dialect consists of a set of dialect-specific operations. Yeah, say in this case, in the case of OpenMP, you would use instead of flat control flow, you have an operation that encodes a for loop. Right? You have transformations on your dialects. So this is code transformations or optimizations that stay in the same abstraction level. And to make everything composable, you of course need conversions between different dialects. So how a modern pipeline would look like is you take some IR as input, and then you convert that to a different kind of IR. On that you do your optimizations and your transformations, and then you convert that again, maybe even partially, to a different dialect or a mix of different dialects. On that you do more optimizations and transformations, and then in the end you convert that to something low level like LLVM. And with that, we're at the end of today's lecture. Thank you very much for listening.